The authors couldn't make it, so it's going to be Kong Fang giving the talk through a video. Here we go. How do you maximize?
I'm Cong Wang from Peking University. I will introduce the paper Sharp Analysis for Nonconvex SGD Escaping from Saddle Point. We consider the following nonconvex optimization problem. We are interested in searching a first-order stationary point or second-order stationary point. To search a second-order stationary point, we must escape some saddles. Look at the three pictures. The three pictures are all first-order stationary points, but only the first and the third picture are second-order stationary points. The stochastic gradient descent SGD algorithm is very popular, especially in training neural networks. The traditional results show that SGD can find the first-order stationary point in epsilon to the power of negative 4 stochastic gradient cost. However, in this paper, we will show that a little variant of SGD can find a second-order stationary point in epsilon to the power of negative 3.5 stochastic cost under suitable assumptions. This is the comparison on the stochastic gradient cost for finding a second-order stationary point. For original SGD, our analysis is sharper than others. However, for all algorithms, the sharpest bound is obtained by the algorithm named Spider, which can achieve a complexity of epsilon to the power of negative 3. This page shows the assumptions in our analysis. We further assume that the objective function is Hansen smooth. The first three assumptions are common in existing analysis for searching a second-order stationary point. To let SGD fastly escape saddles, we define a property named dispersive property and assume that the gradient admits the dispersive property. Actually, it can be considered as a general version of injective boat-shaped noise used in other related papers. So for most smooth noise, such as Gaussian noise and boat-shaped noise, this assumption holds. And we can also remove this assumption, but inject artificial noise such as Gaussian noise during the iteration. This is the definition for our dispersive noise. We first define a narrow property for a Borel set. And we can see the following picture. The dispersive property is defined for a random vector if for any arbitrary set A that satisfies the narrow property. We have the probability that the random vector belongs to A is less than a constant 1 over 4. So you can imagine for almost all smooth noise, it satisfies the dispersive property. Let's look at our algorithm. Our algorithm differs from the classical SGD only on the stopping criteria. We use a ball-controlled mechanism. That is, if X can exist a small neighborhood before K0 iterations, the algorithm will start over and do the next round. However, if X cannot exist the small neighborhood of in K iterations, the algorithm will stop and output the average of the next K0 iterations. We have the following theorem. It shows that when treating sigma, L, and rho as global constants, the algorithm 2 can find a second-order stationary point in epsilon to the power of negative 3.5 cost. How can we achieve a tighter bound? Let us first recall the traditional analysis. The traditional analysis mainly use the gradient smooth condition, see equation 7. So to ensure the momentum descent of the function value, the step size eta should be epsilon to the power of 2. Thus, in each step, the function value can descend epsilon to the power of 4. To improve the rate, we decompose the function into two parts. The first part, the function is near convex. Refer to picture A. Solution techniques for near-convex problem ensures faster rate. The second part is near-concave. So L in traditional analysis reduced to epsilon to the power of 0.5. Refer to equation 8. So both the two parts can ensure a faster rate. In detail, we consider the quadratic approximation of the objective function. Let S be the subspace spanned by all the edge vectors of H, whose edge value is greater than 0, and S perp be the complement space. We define two functions, GS and GS perp. So GS is the convex part, and GS perp is the concave part. In the following, we can separately analyze GS and GS perp. Both the two parts can have a faster rate. Actually, for GS perp, the analysis is similar to the traditional analysis. However, as we have mentioned, L is now reduced to the epsilon to the power of 0.5. For the analysis of GS, we consider an auxiliary update that only perform gradient descent on GS, and then analyze the difference between the two trajectories. And we can also achieve a faster rate. More details of our proof sketch can be found in our paper. Thanks everyone. For any problem, please send email to fangcong@pku.edu.cn.
If there are any questions, you might want to record a video and email them. And that concludes the session. So let's thank all the speakers in the session. Thank you again.